welcome to another video. Today we're going to be doing 236 lowest common ancestor of a binary tree. So given a binary tree, what we want to do is we want to find the lowest common ancestor of two given nodes in the tree. And the definition of an LCA, two nodes P and Q, as the lowest node in T has both P and Q as descendants. Okay, that makes sense. So the LCA of nodes 5 and 1, here is 3, and the LCA of nodes 5 and 4 is 5 since a node can be a descendant of itself according to the LCA definition. Okay, that makes sense. I think I did a similar problem to this before, except the other variation of the problem had allowed you to be able to reference its parent node, whereas for this one, we can't reference the parent's node. One way I'm thinking of solving this with is by checking to see whether or not a certain node has a is P or Q, or whether or not its left children has P, or whether or not its right children has Q, or like P, and same thing with Q. So I guess in order to better explain this, I'll walk through this example over here. So we start off with this tree over here, and we know that the least common ancestor of nodes 5 and 1 is 3. What I'm going to try to do is I'm going to take a look and start at 3, and I'm going to be like, okay, so I'm going to recurse through its left children and its right children. What's going to happen is if the value, if the node 3 is either one of P or Q, then it's going to return true. And in this case, it's not, right? Because it's 3. So it's not P and it's not Q, so it's not that's not going to happen. So the next thing we're going to want to check is whether or not the left subnode, or the left child, will eventually return 3, and whether or not the right child will eventually return 3, whether or not the left subnode will return 5, and whether or not the right subnode will return 1. So it's going to recurse down here, and it's going to go ahead and check, is 5 equal to one of the P or Q? And it is, so it's going to return true, and it's going to recurse back through here. Same thing with the 1 over here. It's going to check to see if it's equal to P or Q, which it is, and it's going to return true. Now, we'll know that something is the least common ancestor where 2 of 3 conditions are fulfilled. Either the left node, one of the left children, the left thing is going to eventually return true. So that means on the left side of whatever the node is at, the left child or anything below it, it's eventually going to return, eventually going to have P or Q. With the right side, we can check to see if any of the subnodes within the right side are going to eventually equal P or Q. And another thing we want to check to see if the actual one itself is going to be equal to P or Q. So if any of these, if any 2 of these 3 conditions are fulfilled, then that's when we're going to actually be able to understand that it's the lowest common ancestor. So if that kind of makes sense, I can go ahead and begin coding it up now. What's going to happen is we can go ahead and we can do a DFS. So we have DFS, we have left, DFS where we have a root, right? And we want to return DFS root. Okay, what's going to happen first is we're going to want to check to see if not root, then we just return false. That's going to be our base case, or our case where it terminates. Next thing we want to do is we want to check to see if node, or if root.val is equal to P, or if root is equal to P. Yeah, because we're being passed in the the actual node itself. So if root is equal to P or root is equal to Q, then we want to return true. Otherwise, we want to do left is equal to root dot to DFS root dot left, and then right is equal to DFS root dot right. If and we want mid, or actually maybe instead of this one, what we can do is we can do a check to see whether or not the mid is equal to the to root equals P or root equals Q. So either one of this will return true. What's going to happen is we can do a check to see if left plus mid plus right mid plus right is greater or equal to 2, because if something is true, it's going to evaluate to the integer 1. So if this is going to be greater or equal to 2, then 2 or more of the conditions have been fulfilled. And at that point, we will know that this is the lowest common ancestor. So then we want to return the root. Otherwise, what we want to do is we want to return the yeah. Otherwise, we want to return the mid or left or mid or left or right. So if anything is there, then we want it to recurse through and move forward over here. So just to do like a quick dry run of this and verify that this works, what's gonna happen? We'll do it with this example now. We'll go to 3. Okay, so P is 5 and Q is 4. Okay, so we're gonna start off at 3. It's gonna be for this side it's gonna be true, and then for this side it's going to be false because nothing's gonna be here. So that's going to be it. None of the conditions will ever be fulfilled where it's on both sides, so that's not going to be a valid answer. Eventually, as we recurse down, we're going to hit 5, and then we're going to see, okay, like, what is the 5's right? Well, the 5's right is eventually going to return true because this is going to recurse and be equal to true. The left side isn't going to do anything because it won't have P or Q. So that means for like the 5, the mid is actually going to evaluate the true because it's going to be equal to one of those nodes. So because these two conditions have been fulfilled, both the mid is going to equal to be equal to true, and the right is going to be equal to be true. Then we know that this is going to be our final answer. So I think this should work. So P and Q will exist in the tree, so we don't have to account for that edge case. All the node values are going to be unique. That makes sense. So let me just go ahead and do a quick run through again, just making sure this is all good. Run this. Oh, okay, small indentation error. Okay. Unsupported operand type. Oh, okay, I see. Maybe what we have to do is, in order to stop this from happening, we want to start off with the DFS root, and then we want to return a res. So we can do like a self or like non or like res equals to none so far. Then we do like non-local res, and then we can set the res. Res is equal to the roots, and then we just return. Yeah, and then from there what we can do is then we can just return res at the very end. Res equal to root. Unsupported operand type. We'll have this return true in this case. Well, actually, we'll have it return false because we just wanted to return the results. So if we do this, all test cases accepted. Let's go ahead and run the submit, and there we go. So the time complexity of this one is going to be O of n because you're going to be going through every single node in the root. And in terms of the space complexity, it's also going to be O. I think it should be O of. I think it should be O of H, but like the worst possible case scenario, if we have like a really sparse tree, it's going to be O of n because at the worst case you're gonna have to be traversing through every single thing to find like the common ancestor. So we have like 5, 4, 3, 2, 1, and it's like all separated like this. It's going to be O of n in the worst case. So we're gonna wanna like make sure that like the worst cases of this one is going to be O of n space complexity, and the average I think is going to be O of h because on average it'll like be recursing down for like the height of the tree itself. So yeah, thank you guys for watching.